Thank you for being here early in the morning. Just a couple of quick announcements. Please do fill the feedback form. If you have been offered reimbursement, please do fill in the bank details. That's also in the feedback form. And during the breaks, you can go and collect your participation certificates. So yeah, without any further ado, I'll hand it over to Sayak.
So this is the last lecture of differential privacy. Is that not working? Hmm? Okay. So we talked about overview of privacy in the first day and discussed different kind of attacks. Oh, I think this is not the correct one. We have to change it. Give me a minute. We gave some overview of data privacy. We talked about different kind of attacks in the first day. Yesterday we talked about differential privacy as an answer, and we defined privacy in a formal way. We discussed some properties. I've talked about one mechanism which is called Laplace mechanism, and show its privacy and utility guarantee. So today we will talk about some more differentially private mechanism, and also one variant of differential privacy definition. This will be the agenda for today. Okay, so till now, if you remember, we were asking queries of the form, what fraction of the population has the disease? So these queries, you can see that the answer of this query are always is always a number, right? So these kind of queries are called numeric queries. So we have our data set. A randomized algorithm take the data set as input. The data users asks the numeric queries like what fraction of the population has disease, and the randomized algorithm to satisfy differential privacy, it returns the answer and perturbs the answer by some noise with the scale of the noise proportional to 1 by epsilon times n. If we do like that, then we have proved yesterday that this randomized algorithm will satisfy differential privacy. Okay, so these mechanisms, right, this kind of mechanisms like that we have discussed, Laplace mechanism, it takes the answer and add a Laplace noise with proportional to 1 by epsilon times n, right? So these mechanisms are called output perturbation based mechanism, because what it is doing, is taking the answer and perturbing the answer by some noise. So this kind of mechanisms are called output perturbation, and this holds for numeric queries. So these are, and also there is one more interesting point for this kind of mechanisms. These mechanisms will be useful only if similar answers have similar utility, right? If two similar answers have different kind of utility, so then we will not be able to add proper amount of noise, because noise was added proportional to the sensitivity of the queries. So if two similar answers have very different utilities, then to make the mechanism private, we have to add a lot of noise, right? So that will hamper the utility of the mechanism. So remember we have proved some utility bound of Laplace mechanism. So if two queries have different answers, two similar queries have different answers, then the utility of the mechanism will suffer very poorly. And so the thing is for different other kind of queries, this property that similar answers will have similar utility will not be satisfied. Let me give an example. Think about this table. So there are two buyers of a good, and think about I am the seller. Okay, I want to sell a good, and there are two buyers, Alice and Bob. So Alice is willing to pay at most €3 for the good, and Bob is willing to pay only at most €4, right? So now what kind of price should I set, right? What kind of price should I set for the good so that I get some profit, right? There are a couple of options for me. Suppose I set the price as €3. There can be another option like €3.01, €4 and €4.01. So now if I set my price as €3, right? So my selling price as €3, could you please tell me how much profit I will get? And I know that there are two buyers who are willing to pay me this amount, but I set price as €3. How much profit I will get? No, think about my buying price of the item is 0. Think about this is some item I have made. So my cost is 0. There are two buyers who can offer me €3 or €4. I set the price as €3. So what profit I will get? €3, right? Because Alice will buy it, right? Now I set the my selling price as €3.01. So how much profit I will get? 3.01 euro. Sorry. Okay, I think I made a mistake here. So let me So let me rephrase this question again. So my buying price was €3, not 0. My buying price was €3. I set the price as €3. So how much profit I will get? 0. Similarly,
Sorry, but won't both Alice and Bob buy it at €3?
So Bob will offer €4.
So I thought you are the seller and they are the buyer, and they're willing to buy for €4.
No. Bob will offer €4. Alice will only offer €3. Okay, so Bob will only offer €4. Bob will not buy it. Bob offer is €4. Okay, so I think I again confused. Okay, so let me get it straight. Okay, so my buying price is €0. Okay, so I got an offer from Alice €3. I sold it, right? So my profit is €3. So now Alice offers 3.0. Now I set my price as €3.01. What will be my profit? And Bob will not buy it in this example. Bob will not buy it. He will only buy after €4 onwards. So my profit will here be 0 because I will not find a buyer. So Alice is only willing to pay €3. I have set my price at €3.01. So I will not find a buyer. So my profit will be 0 here. So the thing that I want to point out here, I have set two prices, €3 and €3.01. Both are very close to each other. Both are very similar prices, right? But however, my utility, which is my profit, is at the first case it is €3, and then in the second case it is 0. Okay, so my answer or my my selling price is similar, but my profit is drastically different in these two cases, right? So there might be queries in this form where similar answers will not have similar utility. think about like same thing will happen here. If I set 4 euro, Bob will buy it, and my profit will be 4 euro. If I set 4.01 euro, Bob will not buy it, so my profit will be 0. So this kind of things will keep on happening in different kind of queries. So what I'm trying to articulate here, that there will be out queries which will have similar answers but do not have similar utilities. These queries can be of non-numeric kind. Think about the queries of the form, which CS theory lecture is popular among the students. Think about you are attending a CS theory winter school at IISc, and you are attending a couple of lectures, zero knowledge proof, matching theory, differential privacy. Which one you like, right? So an instructor can guess based on the attendance of the participants, and instructor can convey his or her feeling to the organizers, and might not, if the course is not popular and the instructor is malicious, you might not get your certificate. So think about this kind of malicious instructor who is trying to guess it from the students, and this kind of queries are being asked. Similar, like what is the most popular AI model, right? Different AI models. So a company is doing a survey, they are releasing about different AI models. So which AI model is used by industry practitioners? Like which price would make the most profit from buyers, right? Which kind of price I set to my selling good where I can get most of the profits. So as we have seen, if I set 3 euro, I will get 3 euro profit. If I set 3.01 euro, I will get 0 profit. So these are like non-numeric queries. So answers of these queries of the form. So the answer set or the output set of this CS theory query is can be different courses like matching, ZKP, and differential privacy. Similarly, answer for the AI model question can be GPT, Llama, Phi, Gemini. The GPT has been designed by, developed by OpenAI. Llama developed by Meta. Phi 2 is by Microsoft, and Gemini is by Google. So you asking this kind of queries, a company can figure out which model produced by different tech giants are popular among the industry practitioners. Similarly, as we have seen, the set of answers of the profit question will be this set. Okay, so let us formulate this. So we have a query. It takes a data set and gives a output set, right? It gives an element from the output set. It takes a data set. The answer can be any one from this output set, right? You might like matching better than the other courses. So each query is associated with an utility function U. It takes a data set and the output set and give you a number, right? For example, which CS theory course is popular, and your answer is matching, and then you will give a score, right? So I like matching with score 0.8 compared to I like differential privacy with score 0, something like that. So what does the utility function tells that how good the answer Y is when the query is Q. So how much you like each course, right? This is just the utility function for the instructors. You have probably given feedback form, you can use this kind of thing, right? So now we define global sensitivity of a utility function. Remember, we have defined global sensitivity for queries last time when we were talking about Laplace mechanism. So now we'll define global sensitivity of a utility function. It's the same definition, that you take a utility function U for two data sets D and D dash. Obviously D and D dash are neighboring data sets. That means they differ by only in one entry. Now what is the compute the utility differences for a particular output Y, right? And find the maximum utility differences over all the outputs Y. This is a global sensitivity of a utility function U, right? So for compute utility differences for two data sets D and D prime for a particular output Y, and take a maximum over all possible outputs. This is the definition of global sensitivity of the utility function. So what kind of differentially private mechanism we can build if my outputs are like this? It's not a number anymore. It's a categorical kind of answers. So matching is one category, ZKP is another category, and price is another category. Alright, so the mechanism that will achieve differential privacy for this kind of queries is called exponential mechanism. So this is our data set, but now I have modified the data set. Instead of, we have a lot of students, they have their address, they have their age, and they have their genders. So these are non-sensitive information, and I have now modified sensitive information from disease to your lectures, the lectures that you are attending. So Alice likes DP, Bob likes matching, Charlie likes ZKP, and Zora likes ZKP. So these are, you can think about your sensitive information, because providing this information might harmfully affect your certificate that you are getting if the instructors are malicious. So dataset is being passed to the randomized algorithm, and algorithm gets the dataset, and users can, or an adversary, here the adversary could be the organizer or the instructors, they can ask some query to the randomized algorithm, and the algorithm will get some answers. This is the overall privacy mechanism of a statistical database. Okay, now the sensitive informations are the lectures liked by the students. So data users ask a non-numeric query that which lecture is liked by the students, right? So this is a non-numeric query. The answer will be, so if we ask this kind of query, the answer will be answer 1, a small y in capital Y. So in this example, the capital Y is different kind of lectures, right? So, and small y is one such lecture. Say answer DP with probability proportional to this number. So proportional to e to the power epsilon times utility of the answer y with respect to the database D divided by 2 into global sensitivity of the utility function, right? So this is, recall, this is the global sensitivity of a utility function, right? So each query is associated with the utility function, and if we the algorithm will return answer y, that means it is returning answer dp with probability e to the power epsilon times the utility of the answer dp divided by 2 into global sensitivity of that utility function. Okay. So this is the mechanism. So for every possible y, we will output every possible y with this probability. Right. So the thing is, if some y has high utility, like if some answer y has high utility, that means u of d comma y is high, then this probability will also be high, right? It is e to the power this utility. So this probability will also be high. So it will be more likely that answer will be returned, right? So if matching has high utility, like that means students liked matching most, then most probably matching will be returned, right? So high utility answers are exponentially more likely to be returned. Okay, so this mechanism is called exponential mechanism because we are taking the utility and exponentiating it with an exponential function. The mechanism that answers choice y from the set of all possible choices is epsilon dp, and the mechanism is given by this. So we will output a choice y with probability exponential e to the power epsilon times utility of that algorithm. So this is the mechanism. This is called exponential mechanism, and this works for non-numeric queries like which lectures are preferred by the students. So let me give a quick proof of this mechanism. So remember, so we have to prove that this mechanism is epsilon differentially private. So for that we have to bound the ratio, right? So we'll compute the probability that when the algorithm is run with the dataset D and comes with some choice y, and we compute the probability when the algorithm is run with the neighboring dataset D dash and answer the same choice y, right? So this each y you can think about our lecture, right? And D is two data sets, where D and D dash is two data sets, and only one person's data has been changed. And we know that if we can bound this ratio by e to the power epsilon, then this mechanism will be differentially private, right? Any question, right? Okay. So we have to bound this, and we know the upper bound on this global sensitivity. The global sensitivity that take the utility function, and for these two data sets D and D dashed, compute the utility for a particular output y, and take the difference between the utilities, and take a maximum over all possible outputs in the output set. That is called the global sensitivity. We assume that this global sensitivity is bounded by some positive number capital delta. It's same as that what we are doing when we are proving Laplace mechanism. Okay, and now we also have our differentially private mechanism that will output y with probability e to the power epsilon times utility divided by 2 into this global sensitivity. I am just modifying the mechanism a bit. Instead of global sensitivity, I am putting 2 into delta because it's an upper bound. So this is our mechanism. We'll output y with this probability. Okay. So now you can see there is a proportionality sign here, right? So can you tell me what is this proportionality constant here? So I have written the probability is proportional to this. So do you have any guess what will be a constant will be here? What will be the proportionality constant here? Any guess? So your hint is, this is a probability mass function. If we sum over all y, there are multiple possible choices, right? Sum over all y, that means we're summing the PMF, probability mass function. It should sum to 1, right? That is your hint. So what proportionality constant should I put here, so that if I sum over all y, it will go to 1, right? Because ultimately it has to be a probability mass function. So any idea here? Okay. So it will be nothing but I will sum this probability over all possible answer choices y dash, sum this and just invert it, right? So this constant CD will sit in front of this, so that if I sum over all y, the total sum will go to 1. Can you see it? So this is our mechanism. Probability of AD equal to y is equal to CD times exponential of epsilon times utility. So this will be our mechanism. Alright, now go back, that what we have to prove? We have to prove this ratio is bounded by e to the power epsilon. So first see that, I will write it descriptively. So probability of AD equal to y it will be CD times e to the power epsilon into u of d comma y divided by 2 delta. Similarly, I will change the data set from d to d dash. So the probability will change to CD dash into e to the power epsilon into u d dash comma y. So this is the ratio now, right? So I will now bound these two terms separately. Okay. So one is this one and another is the proportionality constant terms. We have to bound both the terms separately. So consider this term. So we can write it as, just take the numerator to the denominator to the numerator. We can write this as e to the power epsilon times the utility differences for two data sets divided by 2 delta. Okay. So now how can we use global sensitivity to bound this term, right? Can you see it? We have that global sensitivity is upper bounded by delta. How can we use that? So we'll just upper bound this by just this quantity, that utility differences, we upper bound this by delta and put delta here. So e to the power epsilon into delta by 2 delta, it will be e to the power epsilon by 2. So this term we bound it by e to the power epsilon by 2. Now we need to bound the proportionality constant terms. Can you see how can we bound this? the same technique will apply, the proportionality constants of the same form, only the summation is there, but essentially similar technique will apply. And turns out this ratio of proportionality constants will also be bounded by e to the epsilon by 2. I will give you, take it as an exercise and complete this proof. Okay, so now we have two ratios which are bounded by e to the epsilon by 2. We multiply both together. So our final this ratio of the probabilities for the two different data sets will be upper bounded by e to the power epsilon by 2 times e to the power epsilon by 2, which is equal to e to the power epsilon. So we have proved that this ratio is upper bounded by e to the power epsilon. So now we have proved it for all y, so, and for all neighboring data set d and d dash, so our mechanism will satisfy epsilon dp. So I proved now that exponential mechanism is epsilon dp. Okay. Any question till now? Yeah. Huh? No, compute the u will be given to you. U will be given to the problem statement. No, you do not need to, yeah, u is a function of the data set.
So if it is given to me, then do they already know?
So when you design a mechanism, the algorithm designer will know the utility function. So if the data set is changed, the function value will change, but you know the utility function. Okay, so let me now discuss one more mechanism which works with these non-numeric queries and also satisfies epsilon differential privacy. Okay, so we have our same data set, couple of n individuals, non-sensitive information and sensitive informations like which lectures they like. Similar pattern, algorithm takes queries, non-numeric query q, and gives some answer. So this is another mechanism. Instead of doing this, right? Instead of returning y with probability e to the power epsilon times utility divided by sensitivity, this mechanism, it returns the following. What it does, it first, for all possible output choices, right? For all possible lecture choices, it samples a random variable drawn from exponential distribution. Okay. So what is an exponential distribution? Exponential distribution is a continuous probability distribution with probability density function given by this formula. So probability of a particular choice y is equal to 1 by lambda times e to the power minus y by lambda. Okay. So if you see that for different choices we will get different probabilities. Okay. So what now note that this y should be a real number, right, in exponential distribution. So what we will do, we'll sample a random variable for each choice separately, right? So for choice of the lecture dp, we sample a random variable which is distributed accordingly to exponential distribution. And instead of lambda, we put 2 into global sensitivity by epsilon. So from this exponential distribution, we draw a sample, right? So now we'll do it independently for all the lecture choices. For dp, for the choice of dp, we sample a random variable from this distribution. For the choice of matching, we sample a random variable from the same distribution. So the samples are independent and identically distributed because they are getting sample from same distribution. But nevertheless, we have to do sample again, sample different times for different choices, right? For each choice, we sample a random variable from here and we tabulate it here. For matching, we sample again, tabulate it here. For zero knowledge proof, sample again, tabulate it here, right? Like this for different, if there are 3 choices, we have to sample 3 times. But all are being sampled from same probability distribution. So that's why the samples are independent and identically distributed. And the probability distribution is exponential distribution. Okay, so now we have sampled 3 random variables for these 3 choices, DP, matching and ZK, right? And each choices have their own utility function, right? How much the choice, the lecture is liked by the students, right? Each choice has their own utility function. So for each choice, we'll add the random noise sample that we have generated for that choice to their utility function. Now we'll do it for all the choices. Now we'll return the choice that has this highest noisy utility. This will be our mechanism. So that's why the mechanism called report noisy max. We're reporting noisy maximum utility. So this is a utility. Utility plus zy is a noisy utility, and we're reporting the choice which has maximum noisy utility. So this is why the mechanism is called report noisy max. So any question till now about this? So you understand, right, how the random variables are sampled, right? For each choice from a given distribution, which is an exponential distribution, we will sample sample random variables, right, for each choice, and then we'll add it to the utilities. Okay. So even if the random probability distribution is same, the random samples could be completely different. Okay. So yeah, recall that this is a definition of global sensitivity, and if we do this, then we can show that the mechanism report noisy max is epsilon dp. The proof is similar to the previous one, where we need to bound the ratio of these 2 different choices, and using properties of exponential distribution, basically we need to use a PDF of exponential distribution to show that this ratio is bounded. I will not give the proof, but you can essentially follow the same idea of exponential mechanisms proof and prove the result. Okay, so all right. Okay, so now I will give you another definition of differential privacy. So before that, let us recap what is differential privacy is. If you have forgotten, let us recap this definition for you. So we have a data set to have n individuals. The data set is passed to the algorithm A. The algorithm needs to be randomized. So why randomized? Do you guys remember why the algorithm needs to be randomized? So the reason is, if it is not randomized, then if 2 data sets which differ in only one entry, and the adversary knows the algorithm is being trained using these 2 data sets, then just looking at the output of these two different data sets, that adversary can figure out which data set was used to train the algorithm. And since the 2 data sets will differ by only one individual, the adversary can figure the data of the missing individual, or the individual whose data is changed. So that's why we need the algorithm to be randomized. So we pass the data set to the algorithm. The output of the algorithm is a probability distribution, which is a function of the data set D. And we'll do the following thought experiments. So we replace one data point from the data set, pass the new data set to the algorithm. So we call the new data set D dash. The algorithm will return our probability distribution A of D dash, and this is the distribution of A of D dash. So differential privacy will tell that algorithm A is differentially private if for all neighboring data sets where D and D dash only change in one entry, and for all output S, this relation is satisfied. That means ratio between probability of these two outputs, probability of AD belongs to S and probability of AD dash belongs to S, is upper bounded by e to the power epsilon. Okay. So now we will try to cut some slack to the definition, so that we will tell that, okay, we do not need to satisfy this definition exactly, but we can allow a small error. Okay. We'll try to, instead of satisfying differential privacy purely, we'll try to satisfy differential privacy approximately, right? And the error should be small. That's in that way we'll try to modify our definition. Okay, this is called a variant of differential privacy. It is called approximate differential privacy. Same setup, two data sets changed by only one entry passed to a randomized algorithm, outputs to distributions, and the requirement is to their ratio of these two distributions should be bounded. Okay, so we'll call a randomized algorithm A epsilon delta differentially private, where delta is the error that we are going to allow. Epsilon delta differentially private is for all neighboring data sets and for all outputs. This equation is satisfied. So probability of AD, which is the output when the full data set was presented to the algorithm, belongs to a set S, is upper bounded by e to the power epsilon into probability of AD dash, where only one data point was removed from the previous one, or changed or added. So anything is possible here. This ratio is bounded, so we have till now the requirement of differential privacy, but we will tell that okay, we can cut some slack and allow some small error delta in this bound. Okay, if this thing is satisfied, then we'll call this approximate differential privacy. Okay. So now think that okay, if I put delta equal to 0, what will happen? Any guess? Yes. If delta is equal to 0, then we will get back the original definition of differential privacy. Okay. So delta, allowed delta in this definition is greater than or equal to 0. If delta equal to 0, we will get original definition of differential privacy. So this is the error that we introduce in this definition. So what does it actually in this definition is intuitively telling you that an algorithm A, which is epsilon delta differentially private, this is intuitively it's epsilon differentially private with probability at least 1 minus delta. I don't know why this descent is. This is a type of mistake. Yeah. Epsilon, if A is epsilon delta differentially private, then it is epsilon dp with probability at least 1 minus delta. This is what this definition is actually telling, that with high probability it is P or epsilon differentially private. But with small probability, the privacy guarantee will not hold, right? We are just allowing the algorithm to be not private with some very small probability, but with high probability it will be private. It will be differentially private. That's what this definition is telling us. So note that this definition makes sense only when delta is much smaller than 1 by n, where n is number of data points. So this is only when the definition makes sense. We told that, right? This delta needs to be very small. So it makes sense only when delta is much smaller than 1 by n. So can you guess why this 1 by n is an important quantity? Why delta needs to be much smaller than n? Any guess here? So think about the following case, the following example, right? So I pick a random person from the data set and publish her data on the open. There are n persons. I randomly select one person and just publish her data in the open. So this is my algorithm. I take n person, randomly select one person's data and publish in the open. So what is the privacy guarantee of this algorithm? So the privacy guarantee of this algorithm will be, let's see, it will be 0, 1 by n dp. So why? So first of all, I randomly select one algorithm. So what is the probability of I randomly select a person from these n persons? 1 by n, right? So with probability 1 by n, I am selecting one person and publishing his or her data in the open. So when I publish the data, privacy gets violated, right? So epsilon, what will be the epsilon here? Will be 0, right? Because I published in the open, right? So that means epsilon will be 0 and delta will be 1 by n. So why? Because what delta is telling, that with high probability, right, my algorithm should be dp, right? with 1 minus delta probability, my algorithm should be DP, right? But this 1 by n is the failure probability. So if I put, if I select one person in random, so with 1 by n probability, I'm selecting one person and publishing its data in the open. So my DP guarantee is failed with probability 1 by n, right? Because I'm selecting one person in random and publishing in the open. My DP guarantee, epsilon DP guarantee is failed with probability 1 by n, right? So epsilon will be 0 and delta will be 1 by n. But still it's a, under the definition it's a valid DP guarantee, because epsilon and delta can both take value greater than equal to 0. It's a valid DP guarantee, but ultimately there is no privacy for the person that whose data we have released in the open, right? So think about a subsampling example, right? We subsample some people, and even if subsampling prevent reconstruction, the privacy guarantee still remains. So similar kind of, we sample a person and publish their data is in the open. So we violate the privacy of this person completely with probability 1 by n, right? So to prevent us from this kind of algorithms to be used, we need to put a constraint that we should make delta very, very less than 1 by n. So think about, in practice, delta will be like cryptographically small, right? 2 to the power minus 20 or something. It's a very small number. Okay. Now we need to give a mechanism which satisfies epsilon delta differentially private. Okay, so we have seen that Laplace mechanism satisfies epsilon differentially private, as well as exponential mechanism, report noisy max, all satisfy epsilon differentially private. So now can we design an algorithm which will satisfy this epsilon delta differential privacy? Because those kind of algorithms are useful in practice, because since we are allowing a small slack to the algorithms to be non-private. Alright, recall that our Laplace mechanism for pure differential privacy. Here we have this data, the sensitive information is the person has disease or not. The users can ask queries of the form, how many persons have the disease, and the mechanism answers, reports the answer and add a Laplace noise drawn with proportionality to global sensitivity by epsilon, right? This is our Laplace mechanism. So, and we have seen yesterday that this mechanism is epsilon differentially private, right? And recall the global sensitivity of a query that we have defined. The global sensitivity of a query Q is the difference in output values, right? Answer values QD and QD dashed when I change D to D dashed. Take two neighboring data sets D and D dashed and compute the difference in output values, absolute difference in output values, and take a maximum over all possible neighboring data sets. This was our definition of global sensitivity when we are analyzing Laplace mechanism. Alright, so now we will give a mechanism which is Gaussian mechanism. Instead of Laplace noise, we will add Gaussian noise to the outputs, and we will show, and that mechanism will satisfy approximate differential private. Okay. The same setting, same numeric queries, same sensitive information, similar queries, everything is similar. There is a query which is a numeric query. Instead of perturbing the output by Laplace noise, we will perturb the output by a Gaussian noise. The noise will be sampled from a Gaussian distribution with mean 0 and variance of this quantity. This is the variance of the Gaussian distribution. 2 log 1 by delta into global sensitivity squared by epsilon square. Okay. So what is delta? So that we need to satisfy this epsilon delta dp, right? So if the algorithm designer has been given a choice of epsilon and a choice of delta, he can compute this quantity, right? For any query, compute the variance. Set the variance as 2 log 1 by delta times global sensitivity square by epsilon square. So if I am given this, I can set it like this. Okay, and sample a Gaussian random variable from this distribution and add it to the answer. This is the mechanism. So look, the Gaussian distribution looks like that. I think you all know about Gaussian distributions. So if for different means and different standard deviation, I have plotted the Gaussian distribution. Think about this blue curve when mean is 0 and standard deviation is very small. You can see that the curve is peaked, right? So if standard deviation is small, then the noise that we'll add here will be very small, right? Similarly, if the standard deviation is high, the noise added, so you think about this orange curve, the noise added will be very high. So this is a typical Gaussian distribution with different mean and different standard deviation looks like. And you all are probably aware of the Gaussian probability density function. So basically, we'll sample a random variable using this density function. Instead of mean mu, we'll replace mu by 0, and instead of sigma square, we replace sigma square by this quantity, 2 log 1 by delta into global sensitivity square by epsilon square. This is as simple as that. We have a Gaussian sampling algorithm, who will just call this algorithm, will sample a random noise using this mean and this sigma and add it to the answer. This is our mechanism which will satisfy approximate differential privacy. The theorem here is, you have your mechanism A, which takes a dataset D and the query as an input, and takes the query value Q of D and perturbs it with Gaussian noise with mean 0 and standard deviation, which depends on delta and epsilon. This mechanism is epsilon delta approximate differentially private. The proof is same, exactly similar like Laplace mechanism's privacy proof, and follow the exact similar approach and we'll get that. So I will not give the proof, take it as an exercise. Any question till now? I think we have 5 minutes. 5 minutes? Okay. Alright, so yesterday I actually told you that we have proved a composition theorem, where we told that if you have two mechanisms, epsilon, which both have epsilon differentially private, if we compose these two mechanisms, right, then the composition of the mechanism will be 2 epsilon private. Similarly, if you have k mechanisms, all of which are epsilon private, if we compose all of them, it will be k times epsilon private. So the privacy will add up, privacy loss will add up linearly. That yesterday we have proved, right? So the mechanisms will look like that. A1 is one mechanism, takes the dataset D, outputs, and its outputs in the set S1. A2 takes the dataset D, output in the set of S2. A2 also takes output from A1. Okay. A3 similarly takes D, output from A2 and A1 also. This diagram I have not given, but in general it can take output from A1 also, and outputs S3. Similarly, AK is outputs takes the dataset D, take the output of all previous mechanisms as the input and output in the set SK. This is how the mechanisms are operating, and if we compose all of this, we call the full mechanism as A. Right? Think about you are running a stochastic gradient descent algorithm for k times, where each subsequent round will depend on the output of the previous rounds. Okay. So here is what we assume, that A1 from D to S1 is epsilon delta dp. So now we are considering approximate dp. Instead of pure dp, we are now considering approximate dp. So A1 is approximate dp, epsilon delta dp. A2, whose domain is S1 times D and the range space is S2, it is also epsilon delta dp. That means we are assuming all the mechanisms are epsilon delta dp. Similarly, A3, it can take its input from S1, S2 and the data set, and output is in the data set. S3 is epsilon delta dp. Similarly, AK is also epsilon delta dp. That means all the mechanisms satisfy epsilon delta dp. Now if I compose this mechanism, right, A, which takes D as the input and give output which lies in the Cartesian product of all these S1 to Sk. That is the output of A. A takes input as D and output which lies in the Cartesian product of all these S1 to Sk. That is the mechanism, that is the composed mechanism, right? What can you tell about the privacy guarantee of this total composed mechanism? Right? Think about you are running a stochastic gradient descent algorithm. This will be the final privacy guarantee of a algorithm which runs for k steps. Okay, so here is a very complicated looking theorem. It tells, that's why it's called advanced composition. It takes, okay, let A be a composed mechanism whose input is the data set D and output is in the Cartesian product of all these sets, right? That means A will output this vector S1 to Sk, right, where S1 is output of A1, S2 is output of A2, Sk is output of Ak, right? S1 is small s1 is output of the first mechanism, small s2 for the second mechanism, small sk for the kth mechanism. And we all know all this A1 to Ak are epsilon delta dp. Then we can show that this composed mechanism A is epsilon dash delta dash dp, where epsilon dash takes this form and delta dash takes this form. Okay. So epsilon dash takes this form, epsilon times square root 2k log 1 by delta naught. So delta naught here is some constant. You can think about delta naught is some constant, some small constant. It is not related to this deltas. It is some small constant. So final privacy. Okay, what is happening? What happened? How to close it? Okay, yeah. Okay, so final privacy guarantee of the mechanism is epsilon times square root 2k, just ignore log 1 by delta naught for now, plus k epsilon times e to the power epsilon minus 1 divided by e to the power epsilon plus 1. And also the final mechanism will be approximative dp, where what the deltas will simply add up. Epsilons will not simply add up. In basic composition we showed that epsilons will simply add up, epsilon times k will come here. But here epsilon will be final epsilon will be epsilon times square root k. Final privacy loss will be epsilon times square root k. Ignore this term as of now. I will come to this later. And delta dash, all the deltas will simply add up, right? So deltas will add up linearly. Epsilon will not add up linearly. So epsilon will only add up sublinearly. So that means we can save some privacy over the basic composition theorem that we have discussed yesterday. So now look at the second term. You might tell that okay, in the second term epsilons are scaling linearly, but I am claiming epsilons will only add up sublinearly. So just look at the second term, right? Think about what are my epsilons are. Epsilons are small number. To get a good privacy guarantee, we need epsilons to be small. And then we can approximate e to the power epsilon for small epsilon as 1 plus epsilon, right? This is the approximation of exponential function. Right? These are this Taylor-Maclaurin series. If you do this Taylor-Maclaurin series, you can approximate e to the power epsilon by 1 plus epsilon. So because we are only operating in the small epsilon regime. So I will put back 1 plus epsilon here. Right? So e to the power epsilon minus 1 will be epsilon. So I will put back 1 plus epsilon and subtract 1, it will be epsilon. So the guarantee will be k times epsilon square and divided by some numerator. So ignore about the numerator because it is anyway in the numerator. It will anyway decrease the value, right? And e to the power epsilon 1, numerator is anyway greater than 1. Just replace this by 1, right? So we have k times epsilon square. We have linear dependence on epsilon, but it is k times epsilon square. Now think about epsilon is a small number less than 1, right? So k times epsilon square will be a small value, right? Because epsilon is much smaller than 1. So the thing is, this term will dominate over this term. The first term will always dominate over the second term for small epsilons. So this is a lower order term, and we can safely ignore the second order term for the compared to the first term for small epsilons. So the takeaway is, if we have D mechanisms which satisfy its approximate dp, then you can compose them graciously, where the final privacy guarantee will actually scale and square root of number of queries or number of mechanisms instead of basic mechanism where it was scaling up linearly. Okay, so this is advanced composition, and this is the state of the art guarantee which is being used in most of the machine learning applications right now. So I'll stop here. This is the end of our lecture series. So I'll again give acknowledgement. The materials I have taken from this book by Cynthia Dwork and Aaron Roth. You should read this book, and it's a very good book. There are several courses which are available online. I have taken my materials, but I have learned differential privacy by following this course by Adam Smith and Jonathan Ullman. My material is largely based on their lecture notes. I've also got some inspiration from these courses by Aurelian Bailey, Gautam Kamath, and Salil Vadan and James Honaker. So yeah, I'll welcome suggestions. Please write in your feedback form. How did you like it, and what are the areas you want me to improve on? Thank you. Thank you very much. The slides will be. I'll share the slides with the organizers, and you can access the slides.
Thank you, Sayak. I mean, taking a series of full 7 lectures over 3 days must have been
Okay. Yeah. Welcome back. Now we have Akash Parikh as our next speaker. Akash is a postdoc at IISc, working with Arindam Khan, and he did his PhD from IIT Gandhinagar under the supervision of Professor Manoj Gupta. His interests are in data structures and algorithms, and he recently started looking into algorithms with predictions. So yeah, Akash.
Thank you. You can hear me, right? So today I'll be talking about a BST algorithm named Greedy, and in the title I've written it the cool BST. And at the end of this talk, I assume that you will think that okay, this is one of the cool BST that we have seen. Okay. So let's start. Okay. So let's start the definition of binary search tree. We know that in a binary search tree there is a node, right? The root node, it will contain some key. There is a left child whose key is less than the root, and there is a right child whose key is greater than the root, and this same thing continues, right? So suppose you have an access sequence. Throughout this talk, when we say access sequence, we are assuming that we are just searching in a tree. Some tree is given to us, and we are just searching in that tree. So suppose I have an access sequence that is given to me. Assume for now that this sequence is an offline sequence. We say that a BST is static if throughout the access sequence this tree remains the same, it does not change the structure. Then we say that this tree is static. We say the tree is dynamic if it can reshape it during the access. So suppose if I am searching this 25 and my dynamic algorithm is just that whenever you are searching something, you just put it up in the tree. So suppose I change it, then this tree is a dynamic tree now because I am changing it whenever I am doing some access, right? We say a BST is offline if the whole sequence is known in advance. It is online if you at time t you only know x1 till xt, right? Clear? Oh. And now suppose we want to search a key in a BST, binary search tree, right? Then what we know, the cost of that search is the number of nodes in that root to search path, right? In worst case, we know the length of this path could be n. So if you have n, a sequence whose length is n, then your cost would be n square, right? But we also know that there are balanced binary search trees, right? For which your worst case time complexity is order log n per search, right? Such as ABL tree, red black tree, so on, right? So this is what we all know, okay? Let's start something that few of you might know, few of you might don't know. Self-adjusting binary search trees, right? So it's a dynamic binary search tree. Dynamic means it might change with respect to each access, right? It will reorganize the structure, but without any extra overhead. So you might have seen that AVL tree, right? It also restructures itself, but there is an overhead, right? Balance factor we have to maintain, right? But there is no overhead here. So this type of tree, we say that they are self-adjusting binary search trees, right? One such example is splay tree, right? What splay tree does is that whenever you are accessing, whenever you are searching something in a splay tree, it will take that node and it will make it the root of the tree, right? It will do some rotations, and at the last, the search key would become the root of the tree. So that is the algorithm of splay trees, right?
That takes overhead.
That is not an overhead. That is the algorithm itself. That
Okay.
whatever is coming here, I will just do. So there is no extra memory that I am using.
Okay.
It's a rotation thing, right? In a binary search tree, I can go down the tree, I can do rotations. That would be part of my cost function. That is not an overhead. So the amortized time taken by splay tree is order log n per search. Then it would seem that it is not what we need, right? Because ABL tree also takes order log n time in the worst case, right? Okay. But then why splay tree is important? Let's see this. So let's define something. Suppose let optex be the optimal offline cost to serve a sequence X. So suppose you knew a sequence X, depending on the sequence you made a optimal binary search tree. And for that sequence, whatever the cost this optimal binary search tree has, let us denote this by optex, right? and let cost A of x is the cost on that same sequence x by some other algorithm A, right? Then there is a conjecture called dynamic optimality conjecture, which says that split tree is dynamically optimal, which means split tree is one of the best tree that you can get. It is best for all the sequences. It is a conjecture, not true, right? So it says that for you pick any sequence x, right, whatever the optimum cost is, the cost of split tree is within a constant factor of that, right? This is a conjecture. That's why split tree is kind of important. It is one of the best tree that you can come up with, right?
So split tree is not a single algorithm. It's a like family of algorithms.
No,
right?
it's a single algorithm.
So if you make it a root, if you make the access key a root, so what about the others? Like how do the others change? along the
So the only change would happen along the path,
path? Okay. So
right? So I'm rotating something. So suppose if x is the root and y is the left child. So if I just rotate and make y the root, then x would become its right child, something like this. So it's an algorithm.
Okay.
You are doing some restructuring, but it's not a family of algorithm.
The restructuring is to make sure it's always balanced, right?
No. The restructuring, you can assume that what I want is whenever I'm searching something, I'm assuming that the same key would be searched again in the future. So I want to keep it at the root so that the next time it is searched, the cost is minimal. This is what the thing is.
And you are not height balancing the tree, right?
No.
It's just simple.
Yeah, no height balancing. It might be that some part, one of the subtree is very long.
Okay.
Yeah. Because we are working with an online sequence, so we don't know what the sequence is exactly.
So then that opt is also like on that particular tree itself.
Opt x, yeah. On that, so opt of x is some tree. I don't know.
Oh.
Right. Given a sequence x, using dynamic programming, you can compute opt of x. So assume whatever the cost of opt of x is, that cost is within a constant factor of split tree, right? This is the conjecture. It's not true, right?
Okay, but split tree works with only one tree.
Yeah, split tree is a one tree. Yeah.
What if the tree is like just a path?
No. So you assume that initially there can be an arbitrary tree that is given to you. So initial tree can be an arbitrary tree. Then I feed you with a sequence. Now whatever the sequence is, you go to the, so you search that sequence, you make it the root, and you continue doing this thing till the sequence is over. This is so initially you can start with an arbitrary tree. Yeah. Okay. But now what we want to do? So this is a conjecture for split tree. But now we can generalize this conjecture. We can make a definition out of it by saying that I will say something, a tree to be dynamically optimal, any tree A to be dynamically optimal if it satisfies this property, that tree is best for all the sequences, right? Okay. And there are some definition. We say that a tree is order f competitive if it is cost is within an order of factor of the optimum, and if something to be dynamically optimal, it has to be order 1 competitive, right? Good. So there are two trees which are like contenders for dynamic optimality. Like we think that okay, they can be dynamically optimal, not proven.
Okay, so one doubt.
Yeah.
So dynamic optimality means among all online algorithms, this should be the best, or is it just?
So I have come up with a tree.
Okay.
I'm saying that you give me any sequence of search, and whatever the optimum cost is, my tree would also take the same cost. It would also have the same cost.
Okay.
If I can come up with that tree, then my tree is dynamically optimal.
Okay.
So there are two contenders for dynamic optimality. One we already spoke, just a view of split tree, and the other is greedy. So in this talk, we'll talk about greedy. What this greedy algorithm is actually. Okay. Suppose again I have this sequence xn to x1 to xn. What I can do is that I can represent this sequence in a point set, right? XY plane I can represent. How? Suppose my x-axis represents the keys, y-axis represents time. Time just because we are in the online. So these are just the, so if suppose x1 was key 1 searched at time 1, then I would represent it here, something like this. Suppose if 3 was searched at time 2, so I will represent it like this. 2 was searched at time 3, I will represent like this. Okay? So I can make a point set out of these points. right? Correct. And in the online sequence, if I don't know the sequence, if the sequence is coming in online fashion, then whenever the sequence would come, I will just do this, right? Okay. Now let's see what happens. So suppose in this tree, I am searching for 12, right? So I will start with 15, and then I will go to 10, then I will go to 12. So for searching 12, the keys that I have touched is 15, 12 and, sorry, 15, 10 and 12. 12 will always be touched, right? So now, let's see. So Demen et al., they discovered this thing that in this geometric view, when I'm searching for 12, with this 15 and, so this is just an example that I'm showing, right? The points below 12 can be arbitrary, right? They will form a rectangle with these 2 points, right? So what they discovered that when I will search 12 in a tree, they will form a rectangle with these 2 points at least for our example, right? And what is the property of this rectangle? Let's see. So suppose I have given a point P, I have given a point Q. So here red points means I am accessing those points. These are the points that is given to me, right? If they form a rectangle and there is no other point in this rectangle, so currently apart from P and Q there is no other point in this rectangle. So what can I, so this rectangle, currently I will say that this is an arbitrarily unsatisfied rectangle, okay? To make it arbitrarily satisfied, what I can do, I can add a point here. As soon as I add a point, here adding a point you can visualize as touching something, right? This is a touch point, okay? Let's denote this blue color point as a touch point. Then I can add an extra point. So this is the point that I am adding. It is not given by the sequence itself, right? Then I can make this rectangle arbitrarily satisfied. So suppose if I have this kind of rectangles which are arbitrarily satisfied, then what can I say? So they show that given a point set xp is the red points that is given to you. Okay? Can I find a set y of these blue points such that xp union y is arbitrarily satisfied, right? And the cardinality of xp union y is minimal. Okay. So it's just a word which says that in a rectangle, if I have a rectangle and if there is no other point in that rectangle, then I will say it is arbitrarily unsatisfied. If there is a point in the rectangle, I will say this is arbitrarily satisfied. Just a definition.
So, what does it exactly mean by find a point set y from? So that will be a part of from which set will I choose the points?
You can choose any set. So given these 2 points, I want to make this arbitrarily satisfied. I have added a point here. You can add the point here also, wherever you want. Oh, but at the end, when the whole sequence ends, this xp ends, I want a y which should be minimum number of points that I can add, right? So this is the extra points that I am adding, right?
Also one more thing.
Yeah.
Every pair of points.
Every pair means both red, both blue, and both red and blue. I will come to that. It's not that only I have to satisfy these red triangles.
And what about blue and blue?
They should also be satisfied. I will come to that.
And a pair of points means we'll put those points on the diagonal and see the rectangle which is
Yeah.
parallel to the axis.
Yeah. So if 2 points are axis parallel, if they are like this or like this, then they will not form a rectangle, right?
Yeah.
If they are diagonal, then only they will form a rectangle.
You said something like every rectangle should contain at least 3 points.
You can say. Yeah. Okay.
So if it's axis parallel, you look at the line segment or you won't count it?
If it is axis parallel, then you don't do anything.
Okay.
It's already arbitrarily satisfied because there is no rectangle there.
Okay.
Yeah. We will only add if there is a rectangle which is not arbitrarily satisfied.
Okay.
Yeah. Okay. So what this point set y actually does, right? And here is the cool thing. What they show is this lemma which says that, okay, given this sequence x, this red points to you, you find a set y, right? And the assume this x point set x is some access sequence for a binary search tree. then the number of points that you have added, the blue points that you have added, for the sequence X, there is a corresponding binary search tree with the same cost as the number of blue points that you have added. Right? So this is what this lemma says.
Can you repeat this?
I will explain this with an example. It would be clear. What do I mean? I will just explain this. Okay? So let's see. And how to calculate this point set? For that they are given an algorithm named greedy. Okay? And let's see what this greedy algorithm actually says. So suppose I am searching 6. So 6 I am searching. There is only one point. It is arbitrarily satisfied. Right? Next I am searching 2. So you'll see that 6 and 2 they form a rectangle which is arbitrarily unsatisfied. What should I do? I should add a point to make it arbitrarily satisfied. This is the algorithm that I am talking about. Right?
The point you should add only at like lattice points or.
Yeah. What this adding actually means, in a tree view which is I am hiding from you, there is a complicated tree view to it which I am not talking about. What it actually means that there is a tree in which once I am searching 6 and then I am searching 2, I will touch 6 in that tree, and this blue point exactly mimics that. Okay, that if I search 2 before I search 6, that means I will touch 6 at that particular time. So this is what it says. I will touch 6 when I am searching 2. This is what it means. Okay? Let's see one more example. Suppose I am searching 9. Again, so now you will see that there is an arbitrarily unsatisfied rectangle. It can be with blue and red point also, right? Again, I have to make this arbitrarily satisfied. So I touch it here. Yeah. Right? Again, suppose you are searching 4, then you will see that there might be 2 arbitrarily unsatisfied rectangles, right? I have to satisfy both. So I'll test this point C, right? Similarly, I can do it for other sequence. Right?
So these arbitrarily unsatisfied rectangles will they be disjoint or something? Is there some property like that?
There are properties of this thing.
Okay.
Yeah, but at this point of time, suppose if the sequence ends, you can check, you can pick any 2 points, and there is, if they form a rectangle, there is another point in that rectangle.
Okay.
Okay, you pick any 2 points, right? So this is the condition, and what this saying you is that given this sequence, of course, if I have a sequence of length n, I would have to pay a cost of n, at least n, right? These blue points are the extra cost that I have to pay, right? Okay. Any questions here?
So on the x-axis we have the
Keys.
the sequence items. And what's on the y?
Time. It's an online sequence, right? So at each time, so 6 had come at time 1, 2 had come at time 2, 3, 9 had come at time 3. So it's a time. Any questions?
What is exactly meant by the extra cost?
So in a tree, if you are searching something, right? So you will touch those points, right?
So,
If
so what do you mean by exactly touching these points? Like,
so suppose in a tree view, right? In a tree view, if you are searching something which is at the leaf, and you are starting from the root, so there is a path, right? And you will touch some points in that path. So that touch points, that the nodes that will touch in this path are exactly the ones that I am denoting in this point set here, right? But you don't know what the tree is. I have not explained what the tree is. You don't even need, because why don't you need? Because there is a lemma which says that there is a tree view which corresponds to this cost is there, right? So you don't have to worry about the tree view. That's a very complicated thing. You go with this clean view, right? Yeah. Any questions?
So is this the algorithm? Or
Yeah, this is the algorithm.
Okay, so
So
whenever,
yeah.
whenever like a point comes, this red point comes, you put that like, and now you look.
Yeah, I look all the points below this, and I find all the unsatisfied rectangles, and I add a point.
Add a point to each of them.
At each time, yeah. So in this case, this and this unsatisfied, I added a point here. This and this also unsatisfied, I added a point here.
You could not add a point like at 4, 4.
Here,
4,
4, here,
4, 3, sorry.
here.
Yeah.
You can even add a point here also.
I could add like
Only one point. Yeah.
That's all.
You can even add here. Why we are adding here? Just because we are going up in that time, right? So it will more easy for us to analyze things later on. But you can add a point there also. You can't add a point here in middle. Why? Because then whatever the point you will add, this point and this point again will make an unsatisfied rectangle. So that is of no use. So you have to add something in, at the corner.
So you can also.
Yeah.
Do we need to satisfy all the possible?
All possible. Yeah. All possible rectangles you have to satisfy.
But as you mentioned in the background, it's like we are traversing from one node to another node, right? So, like if we satisfy just one arbitrarily unsatisfied rectangle, so we traverse that way. So why do we need to satisfy all of it?
Because you don't know, right? So when I'm saying that I have to satisfy, so when I'm searching this 4, I'm touching 2 points, right? Why there is 2 rectangles and not 1? Because in that tree, when I was searching 4, the path length was 2. That's why I'm touching these 2 points, right? So you have to make all of this arbitrarily satisfied. Yeah, it's not just one.
So, two doubts.
Yeah.
One, you're saying the total number of points will be something like the total cost.
Yeah, so the cost of this binary search tree is the number of red points plus the number of blue points, and you are done.
Okay, and the greediness comes because you are greedily adding the...
Yeah, the greedy name is greedily. So see, this is not an optimal solution. Assume if I knew this sequence before, red points before, I could have added the point in such a way, blue points, such that my cost is minimal. So I don't know if this is the optimal solution or not. But this is one solution.
Right.
Right? This is what I'm saying. Yeah.
So cost in every round is the number of blue points.
Number of blue points I have
So,
added.
given this, we can figure out which points to touch at which time.
Right. Yeah, you can figure out. Because it's just you can just write a code for it, which can figure out this for you, and you can add all these points.
So, this being arbitrarily satisfied guarantees that I can traverse through the path I found here.
Yeah, correct. Because there is a lemma, there is a proof for it, which we are skipping. Right. Cool. So I think there are too many questions, but again I knew there would be too many questions. So if you want to know more about this, you go and watch Eric Devin's video, and you will know exactly what the things that are hidden from you, what is exactly tree means. It's the same algorithm. He is the guy who has come up with this thing. So you can watch this video, MIT 6.851, right? You will get to know what we are talking about, right? Good. Okay. So let's go further with this thing, right? So now we have a tree which we are viewing it in geometric view, right? And I think till now I am assuming that okay, some of you might be thinking that the tree is actually cool, right? It's not some sort of binary search tree. Let's come to dynamic optimality again. What dynamic optimality is saying us that I want an algorithm which is best for all sequences, which kind of not possible as of now. This is what I am thinking, right? It might be true, we don't know. So let's drop something out of it. Let's not go for all the sequences. Let's go for some specific class of sequences, and let's see what dynamic optimality has there, right? So this dynamic optimality was actually defined in the paper of Slater and Tarjan, where they define splay trees, right? And apart from dynamic optimality conjecture, they define more conjectures also, depending on the specific access class, right? So this access class, so now your X is not an arbitrary sequence, but some sort of sequence which has some properties in it. But there are also conjectures related to this. Let's see these conjectures and can we solve few of them or not, right? So before this, I will just introduce some tools. Let's see how fast I can go. So suppose this is kind of easy. Suppose you have a binary matrix M and you have a smaller pi matrix which is K cross K, right? What I want to denote this function Ex n comma pi. N is why? Because we have an n cross n matrix. You can even expand this to if your matrix is m cross n also. Rectangle is also fine. For us, n is fine. What Ex n comma pi means? It means that given this matrix n, if this matrix pi does not belong to this matrix, it avoids. I will say what the meaning of avoid is. Then what is the total maximum number of ones that I can have in my matrix? That quantity I will denote it by X n comma pi. So let me just show you. So suppose I have this matrix M here, right? And this is my matrix pi. So what M avoids pi means that I take some specific rows, specific columns. I can even change a 1 to a 0, right? That means I don't care about that 1. Can I find a matrix, can I find a submatrix in M which is of pi, which maps pi? So in this case, you can actually find a matrix, which is this, right? If this is my pi, then you can find a matrix that this is there. So in this case, M does not avoid pi, but you can check that it avoids this matrix, right? And will come why these are important. And now what this value means is the following: you take any M, right? You take any M, n cross n matrix. You put as many number of ones as you want. But if that matrix is avoiding this pattern, right, then the what is the maximum number of ones I can have in that matrix is that quantity x n comma 5, right?
Again, if it is avoiding this pattern,
Then we'll see what we want to use this as a tool. But as of now, you know that there is a quantity. If it avoids this, I want to calculate the maximum number of ones in that matrix n, right? And this is some sort of tool that we will use to prove something, right?
okay. Also, one thing, changing ones to zeros in M, we are allowed to do this.
Yeah.
Uh,
Because 1 is some value.
yeah.
I might not care about it, but I cannot change a 0 to a 1. 0 is like there is no information, but now I'm providing some information which cannot be done. If there is some information, I can skip it. That is
You can
fine.
only do a reduction in it.
Yeah. You cannot change a 0 to a 1. Then you can say that
Yeah.
every matrix contains every some matrix also. Fine also. It will also work in M cross N, because I'm just giving you a example here. So that N cross N can be a M cross N matrix also. That is also
And
fine.
pi can also be k over cos.
Yeah.
But if we can change 1 to 0, then we can obviously find this pattern.
1 to 0 you cannot. Yeah. You can you find this pattern even after changing 1 to 0? I don't think so.
You are not allowed to do the other way around.
0 to 1 you can't do. 1 to 0 you can do. Yeah. Okay. So I think this thing is clear. So this is a tool that we want to use, and there are already very good results here that we want to use.
So these numbers will be bounded by like n square or something. M
At most
small
n
numbers.
square. Yeah. At most n square. It cannot be.
Yeah.
So that maximum number of ones you count after changing ones to 0 or before?
I think they will be off by some factor, because this K matrix is some K cross K matrix. So it will off by a K square factor. That is fine thing. So now let's see what can else now how to utilize this thing. Now this greedy matrix that we have defined before, we can also view it as a binary matrix, right? Suppose this was a greedy matrix that was given to me. What I can do, I can change this to a 1, right? I can change this to a 1. I can change this to a 1. Everything, right? So now this greedy matrix, I can view it as a binary matrix. That is fine, right?
How are you changing it to one again?
Just so each of these points, so red and blue, this is the total weight, or this is the total cost, right? This is my total cost. So I can just associate this cost with some 1. So I'm associating with this one. So suppose my algorithm is that I'm just
pushing the cost.
pushing the cost. So I can, with given this view, I can come up with this.
Okay.
Right? So now what is the cost of my greedy algorithm? Is just the number of ones that is there in this matrix, right?
Yeah.
This is the cost of my algorithm, right? So see, from a tree view, you have converted to a matrix view, right? Oh. And there are some known bounds which we will use to prove something. I will at least try to prove one. So suppose there is an n cross n matrix. What this says, if your matrix does not have this pattern, right, we call it pattern, then the maximum number of ones in a matrix can have is order n, right? Very simple proof for this, but we are skipping. So this is what we will use. So assuming we know what these bounds are, okay?
What is that submatrix?
Huh?
Like 1, 1, 1 submatrix.
So n is some n is some m matrix, and 1, 1, 1 is a submatrix, pi matrix.
Yeah.
So
these are 3 cross 2 matrices.
okay. So let me tell one thing. So the places where you don't find anything, you can put as many zeros as you want. So you can put a 0 here, 0 here. Between these two rows, you can add as many rows as you want, and you can put zeros there. It's fine.
Okay, can we do this? Between the, like, there are three columns of one written here. Between the first 2 columns, we add 5 columns of 0, and within the next 2
No.
columns, we add 3 columns of 0.
It has to be consistent.
So it has to be symmetric.
Consistent in what sense?
So what I'm saying is the following. I can add any number of zeros here, right? But as soon as I add this, so I have to be consistent with the dimension of the matrix. N cross n, I have to, suppose I'm working with n cross n. So whatever you expand, you still make it an n cross n matrix. You make it a square matrix.
But that may not be symmetric.
Symmetric in the sense, okay, you are saying that this might be too high?
No.
The
The
shift
one might be closer to.
Yeah, it's fine. Okay, so we don't care what is the distance between them. They can be very far also, it's fine.
And relatively, the top one may be closer to 1, 1.
Yeah, it's fine to us.
And
You
remaining
can do
places
that.
you can fill with 0 or 1, whatever you need.
Only
Just
zero.
zero.
Only
Only
zero,
zero.
not one.
So in that case, if I remove a 1 from that matrix in the middle, is it same as the one on the top? No, right?
Yeah. If
Is this
you just remove that,
Yeah.
yes, it's the
Okay.
same as that.
Okay.
Yeah, right. Because but now you are changing a 1.
Okay.
This is the matrix. This is my pi matrix, right?
Sure.
I cannot modify the pi matrix. I can modify the m matrix.
Sure.
Right?
And what is alpha of n? I don't know.
Okay, so here this is the bound where alpha of n, we say this is an inverse Archimedean function. So assume that for a very large n also, alpha of n is like 2, somewhere around from between 2 to 5. So it's kind of a constant, but it is still dependent on n. So
Log star or
yeah, similar to that. But yeah, it's again very small than log star also. Yeah, so I'll just go a bit fast. Again, this is a property that we'll need. So suppose I see 3 blue points which form this kind of pattern, right? Then what I can guarantee is that, so not in the dotted lines, there would be some point in this rectangle. This is the input guarantee that I have. If I can see 3 blue points of this form, then I know that in this rectangle there would be a red point. Take it that this is true. Okay. If I see something of this form, again I can say that okay, in this there would be a red point somewhere. It can be anywhere. It won't be here. It won't be here. It can be here also. I just put it here.
No, sorry. In A comma T1
A comma T1, yeah.
and B comma T2. So in the rectangle formed by these 2 points at the diagonal.
Right.
So shouldn't there be a point in it that
We are skipping few points. I'm saying that I am projecting few points out of this my greedy matrix, which have this pattern, right? There are many points. So there might be point here also. There might be point here also. There might be point here also. There may be many points. I'm just looking at 3 points.
Okay.
And now what my claim is that if you look at any 3 points which make this kind of pattern, then there would be a access point inside this rectangle.
And why should there be red?
Because that is an access point, access. So that means there would be an access point. There would be a red point there. Yeah.
So it should always be on the lattices, right? So how
We are skipping here, right? There might be some point which is here also. We are not taking it account.
That's a claim that there's a red point.
Yeah, there is a claim. You just take it that I am saying that this is true. Okay. For this also it is true. So if you can see this kind of pattern, assume that there would be a point in this rectangle. Just take it. This is true. Okay. Very easy to prove, but I am just skipping. Now let's see what we can do. So the tools and the everything is clear, right? I will just try to prove one thing. This should not take much time. Okay, let me just skip all this. Let me just say. Okay. So what we want to do is the following. So we want to partition our these blue points. We have many blue points, right? In that greedy. So we have many blue points. We want to partition them, right, into 4 sets. How we partition is the following. If I see a point, blue point, which have a red point below it, and which have a red point to the left of it, then I will say that this is a bottom left point. This blue point is a bottom left point.
Bottom left.
Yeah. So there is a point below it, there is a point, so there is a point below it, and there is a point left to it. So bottom left point, right? Similarly, I can define a bottom right point, right? And similarly, I can define top left, top right. And again, you can verify that they don't intersect with each other, right? So there will not be a point at any point of time. So I will pick a point, and it would be, I would either classify it as a top left or bottom right or top left right.
So this sort of thing won't happen that there is a red point and on top of there is a blue point, and in the blue point two sides there are two red points. This sort of structures won't happen.
Why cannot happen? Because what the red point means? Red point means I am accessing at that time. You cannot access two points at the same time.
Yeah, that's
So that this cannot happen. This is correct? Understood? Okay. Let's see. Again, this is, I will just talk about the post order conjecture. So what is a post order? You might have seen what is a post order. Given a binary search tree, you traverse it in a post order. What is the post order? Left, right, root, right? This is the post order sequence, right? So you take a binary search tree, you apply post order to it, you will get a sequence out of it, right? We say that this is the post order sequence, okay? And alternatively, you know, in the geometric view, what you can say that this, whatever this X is, it would be a post order sequence if it avoids the pattern 1, 3, 2. What it means is the following. So you see all the red points which are there, there will be no red point of this pattern. So 1, 3, 2. So you just see all of your red points. You will not find 3 red points which look something like this. What it basically says, if I search something here, if I search something here, I will not, my sequence is such, I am sure that there will be no point which I will search here, right? So this is the guarantee which my sequence gives me, right? So this is a property of the sequence, right? This is a property of post order sequence.
this is called a 132 pattern.
132 pattern. Okay. And what is the conjecture? The conjecture is that can you find a tree for which you can solve this sequence for all sequence which are of post order sequences? Can I solve it in order n time? You can come up with some tree, but the question is, can greedy or splay do it? Because they are the contenders for dynamic optimality. We only are concerned with this 2 tree. We don't bother about other trees, right? So this is the conjecture. Let's see. So for splay tree, nothing is known. It's just like n log n, which is kind of trivial. You will get n log n. When the tree, again, here the important, again, the one of the things that I'm skipping is there is something called an initial tree that you start with, and your cost might change depending on the initial tree, right? So when the initial tree is empty, then for splay tree you can get an order n cost. But what we want to do, we want to do it for arbitrary tree. For greedy, there was something which is known, n2 raised to alpha n, which is again kind of optimal because 2 raised to alpha n is a small quantity, right? But let's see, can we actually prove this conjecture? Okay. And it turns out it is very simple to prove this when you have all these things that I have defined earlier. Very cool proof. Again, so let's prove that I know I have 4 sets, bottom right, top left and all, right? Let's talk about bottom right. I will say that you take all the bottom right points, right? You will not find this kind of pattern among them, right? How? Let's prove. So this is, all these 3 points are bottom right points, right? So there is a bottom point here, there is a right point here, right? And earlier I have shown you that within this rectangle there would be a red point somewhere. You assume that it is here. I am assuming because I want to keep it there. It looks good. But now this is a contradiction because I know my post order sequence cannot have this kind of pattern. right? So that means BR cannot have this kind of points. And now you go and apply that tool that okay, BR does not have this kind of pattern, the number of BR, I can bound BR with order n, correct? Let's talk about BL, bottom left points. So I have a bottom point here. Again, in this rectangle, I am sure I will get a point. Yeah. So assume this is that point, right? And again, I have already shown you that if you take 2 points, there would be a point in this region, right? But now the proof is somewhat this. I know that this is the bottom left point, so there would be a left point which is there, right? Since there is a left point there, I know there cannot be a this cannot be a point here. There cannot be a point here, right? Because at a line there can only be one red point. So this point cannot be here. So you might claim now that okay, this point might be here, right? But this is again not well for us because this is not giving me that pattern. But now I'm saying that no, this point cannot be here also. Why? Because then this point and this point will make this rectangle, right? And I can keep doing this thing, right? So that means.
Can you just repeat this?
So I know that this point is a bottom left point, so there is a left point here. But I also know that within this rectangle, there would be a red point in this rectangle. Assume that red point was here. I am saying that this red point cannot be here. Because why? Because in a line, there can only be one red point, which is already here. So this cannot be here. Now you can say that, okay, this might not be here, but this can be here. It's a rectangle, it can be anywhere in the rectangle, right? Now I am claiming that, okay, if this is here, then I can form another rectangle of this form using these 2 points, this point and this point, right? And I will say that okay, there is a rectangle in there, but you already know that there will be no point in this region, right? And if you just keep doing this thing, you can do it in as many times as you want. So what we can claim from this, that there would be a point in this region here, and now you will get this pattern. Okay. So bottom left avoid this pattern. Again, you know that bottom left is ordering. Let's see top right.
Yeah, can you put it in? So in the proof when we said that there will be right, like the red point will be right, why can't the same argument why can't we apply the same argument here that we can do this inside numerator? Like let's take the rectangle.
Yeah, you can do this. You can do this. But again, I'm skipping few things here, which can be shown that again there are more properties which I have not given. Because of that, it would be here. You cannot do infinitely because your sequence is a finite sequence. Okay, this n is a finite thing, right?
Can you explain what bottom left means?
Bottom left means so you take a blue point. There is a red point below it, and there is a red point to the left of it.
Okay.
That is the bottom left. Let's see for top right. I'll just go fast because I'm out of time. So let's take this point. There is a top point to it. There is a right point to it. Within this rectangle, I will find a point. You take the point anywhere. Sorry, that point cannot be there, right? Because in that line, then there will be 2 points. So apart from that, you take it anywhere, you will form this pattern. So again, bottom, top left, top right is also order n. Again, similarly for top left, let's take the top of this. Let's take the left of this. In this region, you will find a point. Again, by the previous argument, there would be no point here also, so you will find a point here. Again, this will give you this pattern. For all the 4 decompositions, you found that okay, they can be bounded by order n. So that means overall you can bound this cost by order n, right? So you prove the conjecture for this case. I think I'm out of time, so I will skip few things. But yeah, this is all I have. I can share the slides, or if you want, you can just see Eric Clement's video. This might not be there, but at least for something you will get something. Yeah, let's skip this. Thank you. Yeah, if you have any questions, you can still ask. I think 1 minute.
Can you explain that in traditional
What?
I think he did his integrated MSc at NICER Bhubaneswar. And today he's going to talk to us about algorithms for unmanned search and rescue operations. Over to you, Prahlad.
Okay. Let me just make sure everything works. Okay, great. So, well, I initially wanted to talk about algorithms for unmanned search and rescue operations, but we had a bunch of nice conversations yesterday, and I decided to modify it a little bit, and we're going to be mostly talking about TSP, and I wanted to drive home some ideas for approximation algorithms from yesterday. But it is still loosely related to the title of the talk, so I'll spend the first 5 minutes convincing you that what I'm actually going to talk about is the title of the talk. So motivation. One nice thing is that this problem can be stated in the first slide. How do we search for something quickly when we have imperfect sensing capabilities? You can think of many reasons why you'd want to study such a problem, but this is my favorite example, which is of searching for lost glasses. Anybody who's worn glasses has gone through this before at some point. Let's say this is your apartment layout, your glasses are actually in this dresser here, marked with an X. You obviously don't know that, and what you want to do is to find them as quickly as you can, right? You have a Zoom meeting to attend, and you want to get there as quickly as possible. You would search stuff many times, right? Because you're not wearing your glasses, even if you search the sofa once, you might not find it even if it's there. Or if you search the dresser once, you might not find it even if it's there, right? So you might want to search the same place many times. Obviously, there's a cost in moving between the desk and the sofa and so on, right? Which is the distance between the both of them. There's also a cost to search a particular region, right? There's a cost to search your desk and possibly a much bigger cost to search your sofa, right? Because of how it's arranged and so on, right? So all of these exist. But this is only a nice example. There are actual real-world applications for this. This is a recent paper I had with Nilanjan, Joe, Michael, and Gwen, where we talked about, we applied the same idea to searching buildings. So this is actually a map of Stony Brook, the university campus, and these are the buildings, and we essentially say how many times you need to search a particular building to find somebody who is trapped in one of the rooftops, right? So the cost required to search a roof is going to be roughly proportional to its footprint, right? So this is the
So the number of searches is like the number of people in it at a time proportional to that.
No. So this is the number of searches is what we actually output. So like I said previously, you might want to search the same region multiple times because there's a probability that you miss it the first time you search it, right? Therefore, if I'm given this building, so for example, this small one, you might want to search it many times because the probability that the person is there might be high.
So, but how did we exactly assign this value to that building?
I'm not telling you that. We designed 3 algorithms which I'm not going to talk about at all.
Okay.
So this is the output of the algorithm. Finding this is hard, and therefore we're not going to talk about it in this talk.
Is the probability known to the algorithm?
Great question. The input for the algorithms that we have here is your input graph, essentially, that you know previously. Then it's also the a priori probability distribution of where the target is. So that is also known previously. We also assume that there's a false negative probability, and that changes based on which building you're in, right? So essentially, if you're in a building which looks iffy from the top, it might be harder to find somebody when you're flying over using a drone or something, right? So you have different beta eyes depending on what building you're in.
So what is probability of 5? So what is
Okay. So this is a schedule that I will not define in this talk, but essentially what this says is that the best search schedule to find this target is about 1, and we find that using something called an integer linear program that we designed. We also design 2 heuristics. One is based on an exact algorithm, but that is about the optimal that you can get. And there is also a very obvious greedy algorithm that you can design that is not as good, but it runs much quicker. So this is essentially what is the probability that you find the target within a particular time. So you don't have to understand this slide at all. I just wanted to show nice photos.
So, what about in the question in general? So, you said we want to search things multiple times. So, I want to search it like let's say 3-4 times. Would I need to go back and come, or can I just do the operation repeatedly at the same place?
Great question. We proved that you never need to come back, and that's actually non-trivial. Because if you think about it, and this is actually in my very last slide, if you think about it, the probabilities change as we conduct the search, right? Bayesian update rules, if you guys have heard of that. If I say that the probability that it is at the sofa was, whatever, 30%, and then I search the desk and I don't find it, the probability that it's at the sofa now, based on what I did, is not 30% anymore, right? It'll be whatever, 35%, whatever, right? Therefore, it is not very clear if you would actually come back to a place that you already left, right? And we show that you never need to do that. Okay. And that would only work in whatever, the Euclidean plane or metric spaces in general. So it uses triangle inequality, but yeah, great question. Okay, I spent way too much time on this. Let's actually go to the formal problem statement. If you didn't understand the last 3 minutes, that's okay. Doesn't really matter. It'll just something. Okay, so let's actually formally define this problem. This is a vague statement. How do we search for something quickly, right? What does quickly even mean? So we have 3 main objectives that have been studied. So this is a field that's been around since World War II. So a lot of people have looked at a lot of things. So the first one is essentially algorithms of the type you guys have seen before, right? Worst case analysis. You want to minimize the maximum time required to find the target. Okay? That is the first objective that you can have. The second objective is minimize the average time or the expected time to find the target. Next is when you want to maximize the chance that you find the target, if I'm giving you a bound on the time. For example, in the glasses thing that I said before, if you need to get somewhere in 10 minutes, you don't have forever to find your glasses, right? I'm going to tell you that, okay, you have 10 minutes, do the best you can, right? In that particular sense, the best you can is essentially to maximize the chance or maximize the probability that you find the target, okay? We are going to make a few assumptions in this talk. I'm going to forget the idea of being imperfect. I'm going to just talk about a perfect searcher, in that if I'm at the point where the target is, I will find the target. Okay? That need not be the case. In most practical applications, that is not the case. And we will look at the first objective for most of this talk. Probably 2/3 of this talk, we are going to look at this particular one. Minimize the maximum time required to find the target. Okay? This turns out to be exactly a problem called traveling salesman, right? So a target is hidden in one of a given set of points, let's say on the plane, or if you want to be fancy, in any metric space, right? What you want to do is to minimize the maximum time required to find it. You have a perfect searcher, and therefore this essentially just becomes find the shortest path that traverses all the points. Right? Cool. So let's actually look at the traveling salesman problem for most of this time. So here's the problem statement again, but this time I've drawn the complete graph on these vertices just because it's easier to think of moving along these edges, right? So there are many paths that you might want to consider traveling along, right? Here's one, here's another, and here's one more. Can anybody quickly tell me how many paths there are? I heard n factorial, I heard some 5 something. Oh, yeah. Right. So you have n factorial many points, right? Which is just the permutation of the n points. Right? So n factorial for people who don't know is too many. That's how much it is. Right? So therefore, we can't just list out all the paths and pick the shortest one. Right? That's not going to work. N factorial is much worse than 2 power n even. Right? It's about n power n. So therefore, that's horrible, and we won't do that. What we'll actually do is first look at an approximation algorithm for this. Okay? I will define it loosely as we go along in the talk again, even though we briefly talked about it yesterday. So, okay, let's get back to this. We need to find the shortest path that connects all these vertices, right? Now, note that the shortest path that connects all the vertices is larger than the smallest weight subgraph that connects all the vertices. A path is a subgraph. The shortest path is therefore bigger than the smallest subgraph that connects all the vertices. Right? Everyone good with this? This is essentially, this is the foundation of everything that we're going to talk about. Oh, again, feel free to interrupt me anytime, right? There's no reason for me to finish the talk. I'd like to get deep instead, okay? So, we're good with this statement, right? Okay. So, let's actually drop some edge weights. These are based on, I just plotted this in GeoGebra and it threw me some numbers. These are approximate. This should be some 4.24 or something like that, but whatever, good enough for us. Okay? So, these are edge weights, and what we want to do is to construct the smallest weight subgraph, because we actually don't know how to construct this smallest path. That sounds hard. So therefore, I'm going to say I want to construct this instead. So the smallest weight subgraph, how do I construct this? If anyone would want to guess. Yeah.
So we take a list of the edges when its weight is increasing, and we choose the edges greedily, and when we see that it's not connecting any new vertex, we don't take that edge. We take an MST obviously.
Yeah. Okay. So right. So that's essentially what it is, right? We're going to construct an MST of this, and for people who haven't seen that before, I'm going to show that what we're going to construct is indeed something called an MST. But if you forget all that, the easiest thing to do always is to say that you iteratively pick small edges. I want the final subgraph to be small. Therefore, the most obvious thing to do is to say that, okay, let me pick small edges, right? But remember the goal? The goal is to connect all vertices, okay? So I will iteratively pick small edges so that I move towards the goal, okay? So let's do that. I'll pick the smallest edge first, which is this guy. And then the next thing I will pick is this guy. So am I progressing towards the goal? I am, right? Because I've now connected two vertices, or kind of seen two vertices that I hadn't seen before, right? In the red edges, I only connected V1 and V3, but now I have two more vertices that I've connected, okay? So this is progressing towards a goal. Note that these guys aren't connected yet, right? At the end of the day, we wanted to connect all of these guys. But that's okay. We'll get there when we get there. Thankfully, when we get there is the very next step. Even though this edge doesn't actually connect or see any new vertices, it progresses towards a goal because it connects a bunch of stuff that weren't connected before. Correct? So you would pick this guy. Would you pick this guy? You would not, right? One, it does not connect any vertices, new vertices. It doesn't see any new vertices. And for the vertices that it's seen before, it didn't connect anything new. Correct? So you wouldn't pick this. Would you pick this? You would not. Same story.
Isn't this basically Christmas algorithm?
Yes, but I haven't said the name. So yeah, and finally you would pick this, and that would be that, right? We've connected everything, and this is the subgraph that we get. So this is what I said is going to be important, right? That the shortest path is larger than the smallest weight subgraph that contains all vertices. We'll give these things names. So MST star is going to be the weight of this guy that I constructed. Okay. So MST is the minimum spanning tree, which is the name that people give to this guy. Minimum because it's small, spanning because it connects all vertices, and tree because it contains no cycles or whatever. That doesn't really matter. We don't care about the tree part of it. Okay. So the TSP star is going to be an optimal path. Okay. And these guys is just the size of those things. Okay. Cool. So all that we've said is the size of the MST, the optimal MST, is at most the size of the optimal TSP. Okay, good. So here's the issue here is that how do we construct a path from this? So if we use this tree, essentially, if we want to get to V4, we can't come back to it, right? So this degree 3 vertex is easy. So, okay, let's say I go from V5 to V2 to V3, and then what do? I have to pick one, right? And I don't really know what to pick, okay? So therefore, what we do is double the MST, which is essentially giving us a way to backtrack, right? If we went to V4, then we can come back to V3, right? So that we can get to V1. Essentially, that's roughly the idea. I've drawn the edges like this just so that they don't overlap, and you can actually see what I'm doing. So
if it's on the plane, like just taking the hypotenuse will be better than by triangle inequality. Instead of doubling the edges, I would rather just take the hypotenuse and go to something.
Yes, but the thing is, to take the hypotenuse, you need to do this first because you need to figure out what to take the hypotenuse to.
Okay.
Right? So, and that is essentially what we're going to do now.
Okay.
Right?
Achha, why don't we double the edges only for those vertices which have odd degree?
We could do that. Well, iffy, because one side can have even degree and one side can have odd degree. right? So when you do that, then the number of odd degree vertices could remain the same. So therefore it's not clear how you would do that, but you can do something similar. You can do a similar trick and improve on what we are doing here, but it's just slightly more complicated, and it's complicated enough that I'm not talking about it here.
But doubling everywhere gives us a way to backtrack to exactly from where we came, and not just leave that vertex.
Yeah.
As in even degree, but here we can.
Yes, and that is the property that we want.
Yeah.
Okay. So what we'll do now, what we'll do now is to make a tour out of this, right? But what I mean by that is to visit all vertices, right? Which is what we wanted. Okay. It won't be a path yet. That's okay. Let's make a tour first. Let's visit all the vertices first. So that's actually easy enough to do. We'll just follow the edges like follows. So let's take V1, V3 first, then we'll go to V4, come back to V3, then go to V2, come to V5, get back to V2, and then to V3, and then to V1. Okay? So I've given you a tour. Great. I visited all vertices. Now what? Well, this is not a path, right? So let's make a path out of this. But before that, I want to actually talk about something. I'll call this the doubled MST. Okay, some name, who cares, right? DMST. What is the size of DMST star? Right? Obviously, because we took an MST and then doubled it. Right? Okay. Recall this particular fact. The MST star is at most the TSP star size. Okay? So now, if I can construct a path, if I have not done this yet, let's say I can construct a path whose size is at most this guy. Then, what do we know? Use the first equation, you get this guy. Now use the second equation, you get this guy. Right? You can stare at this for a bit. I'm saying that if I can construct a path whose size is at most that of the blue MST, doubled MST, then that guy actually is at most twice the optimal TSP path. Okay? Everything that I've done here was easy to do or easy to compute. Right? What did I do? I ordered the edge lengths, which takes n log n or something, right? Or n squared log n. And then I just pick stuff iteratively, which is like another order m time. And then I doubled it, which was easy enough to do. Then I actually gave, okay, I hope I didn't break something. Okay, all good. So, and then I only showed here an ad hoc way to get the tour, but that's actually easy enough to do, and I'm not going to prove that. So everything that I've done here essentially can be done quickly. If I can also find this TSP route, TSP path quickly, then in polynomial time, I'm giving you a path that is at most twice the optimal path. Okay? And not only is it polynomial time, it's actually fairly quick. Right? So it's like actually implementable polynomial time. Okay, good. We will start at this a little bit later again, but this is the main takeaway slide. Okay, so let's actually construct a path from this guy. Okay, so I'm going to construct the green TSP path from here. First thing I pick is the first edge of the tour. I mean, nothing too fancy. There is nothing that violates it being a path when I pick the first one. So that's what I do. When I do this, note that my thing so far is at most a double MST, Obviously, I've taken an edge from the doubled MST, right? Therefore, the length of that guy is at most the double MST. Next thing I do is pick the next edge. Again, nothing too fancy is happening here. I can do this and still be within the MST, doubled MST star. What about this guy? Would I pick this? I would not, because this is not a path anymore, right? You get back to V3. So what would I do? Take a look at this sequence. I'm at V1, then I went to V3, then to V4. I don't want to get to V3 again. I want to skip ahead and go to whatever I have not seen before, which is V2, right? So I just scratched it out from this list. Okay? Now there is something iffy happening, right? So far, we'd only picked edges from the doubled MST, right? Suddenly, we're saying, well, you can pick this edge of the graph, right? Or, yeah, so this edge of the graph. And this is my length. I can't directly write this is less than the doubled MST anymore. We have to be a little bit careful. But thankfully, we don't have to be too careful because it's not that hard. This is less than this plus this.
So, are we assuming the graph is complete?
The graph is complete because I've just taken stuff on the plane, right? So these are just points on the plane. You can move between the points in any order you want, right? So the graph that I imposed is just for scenic beauty, right? You really only have the point on the plane. Right? So this is less than this plus this because we are inside whatever, we are on the plane and triangle inequality is a thing. In general, as long as triangle inequality is a thing, this thing works. Okay? Spaces where triangle inequality is a thing are called metric spaces. Okay? You don't really need to know the specifics of it. But I know there are a bunch of people here who are from the math background who know a lot about it. So, anywho, this algorithm works for general metric spaces. Anyway, so because this is less than the edges that I've made with dotted lines, and these dotted line edges are actually from the DMST star thingy, I can still write this thing down. Okay? Everyone with me?
You haven't necessarily applied a better bound here. 2 is still 2.
Yeah, 2 is still 2. I'm not doing anything fancy here. My goal is to get 2. Okay, good. I can complete this fairly easily because the next thing on the list is to get to V5. Once we get to V5, we have nothing else to worry about. Because we visited everything and we have a path. And the length of the TSP path is at most DMST star. Okay? Recall that this is what we wanted. Okay? So, from before, if I can construct a path that does this, then it is at most twice the worst or the best path I can get. Okay? Good. So this is what we have, and therefore we have 2 approximation algorithm for traveling salesman. Okay? So I've given you an algorithm roughly that always produces a path that is at most twice as bad as the optimal one. Note that there is an at most there because all of these were less than or equal to. You could get better, but you'll never get worse than 2. Okay? Cool. From now on, that's going to be most of the math portion of the talk. From now on, I'm going to mostly just give examples and talk about what you can do, right? So in about, I don't know, half an hour or so, we've given a 2 approximation algorithm for TSP. What's kind of surprising is that you can't really do much better unless you use very heavy machinery. So someone was kind of alluding to this, that you can essentially modify what we did a little bit to get a 1.5 approximation instead. Instead of a 2 approximation, instead of doubling the MST, you can, so essentially we double the MST so that we can construct a tour, if you remember. Now, to construct a tour, you don't actually need to double the MST in full. You can only Eulerian tour, not Hamiltonian cycle. Hamiltonian cycles are very hard. Eulerian tours are easy. So you just needed to construct this tour, and which is called an Eulerian tour because some dude in the 1600s decided to name it after himself. Anyway, so to construct that, we just needed even degree vertices, and to do that, you just convert the odd degree into even degrees by being a little bit smart. So this was done in the 70s, and you get a 1.5 approximation. And this again still works for general metric spaces, right? We didn't use any property of being on the plane. We just want a triangle inequality. Okay? So this gives you a triangle inequality. For general metric spaces, here's breaking news. This is from 2021. It is still the journal version is still under review. You can get a 1.5 minus 10 power minus 36, which is 1.49999, and many more nines. This is essentially state of the art. 1.5.
But this does tell us 3 by 2 is not it.
3 by 2 is not it, which is why this is a big deal. It won the best paper in soda in 2021. Okay? People who found this, Anna Carlin is a prof. I think Nathan Klein is a PhD student. He's going to get placed very well. Yeah, this is a big deal. Does it really matter? No. Is anybody ever going to use it? No. But this is a big deal for theory people. What was also a big deal was this. So in 2000, for specifically Euclidean, or if you are in R2, you take points on the plane. Two people came up with an algorithm that says that if you give me any epsilon, okay, give me an epsilon greater than 0, I can give you an algorithm that does 1 plus epsilon approximation. Okay? So this is called a p-task. You don't really need to know what that means. It just says that whatever epsilon you give me in polynomial time, I can find a path that is at most 1 plus epsilon away from the optimal. Sanjeev Arora and Joe Mitchell found this essentially within a few weeks of each other. Both of them got the Gödel Prize, which is something that a couple of people briefly mentioned even yesterday. It's a fairly big prize in computational geometry, in theoretical computer science in general, for useful results. In my opinion, this algorithm is also practically useless because it runs in about n power 100 over epsilon time or something like that. Okay, I don't think there's been any implementations of either Joe's or Arora's algorithm yet. So this is still honestly the best you can do in approximation sense, and we almost covered it in 30 minutes, right? Which is wild because this problem in general, TSP, has been studied essentially since the 1600s, right? Because it's extremely natural. And the best we have is essentially 3 over 2. Okay. What about...
I have a question.
Yes, please.
So, for Euclidean metric, it's easy for approximate it, like 1 plus epsilon is possible. Why is it so difficult for matrix spaces, general matrix?
That's a great question. So it turns out that we can use something called, I think the main thing is like something called a planar separability theorem of some sort. Essentially, it turns out that Euclidean spaces have lot more nicer properties than general metric spaces, which you can exploit to get better algorithms, for them, right? So metric spaces are of course much more general than Euclidean spaces, and whatever works in general metric spaces works in Euclidean plane, but the other way is not. Okay, good. What about, so we just talked about approximation and all that jazz, right? What if we can just do it in polynomial time? Well, yeah.
Sorry, is there any, like, so the plane is like 1 plus epsilon is the thing, it's known. Is there any lower bound that's known for the geometric spaces? Not metric spaces, general metric spaces? Or
Nope.
Two.
Yeah. From what I understand, there's no lower bound. So 3/2 was what people thought you could do, and then they broke it. They're going to win a prize, for sure. And so no,
There's no lower bound.
from what I recall, I don't think it's even APX hard.
Oh, okay.
But yeah, APX hard means that we haven't ruled out a 1 plus epsilon for general metric spaces, from what I understand. Okay, so can you actually do this in polynomial time? No, because if you could, then the two people I mentioned before wouldn't have got the prize. So it's hard. It's the traveling salesman, even in the Euclidean sense, Euclidean setting, is hard. And like I said, there's an obvious n power n time algorithm. Anybody know what that is? Right. So we said that there are a total of n factorial many paths, which is n power n. List all of them and find the smallest one. That's fairly obvious. You can do, using dynamic programming, a 2 power n algorithm. I believe that most of you would have seen dynamic programming before. I will leave this as an exercise to figure this out. This was done in the 60s, so it's fairly ancient. So the proof, or the algorithm, is actually very easy. So you can do 2 power n. Well, it's actually 2 power n squared, but when you're dealing with 2 power n, who cares about the n squared, right? So it's about 2 power n. Okay? And I will let you guys design this by yourself. Can we do better? We don't know. Can we do better than 2 power n? We don't know. If you solve this, you will also get a prize. Okay? TSP, in my opinion, is the most fundamental problem in theoretical computer science, or computer science in general, right? If you say anything non-trivial about it, it's going to have far-reaching consequences in applications that you wouldn't think of. So, which is why it's such a big deal. Okay, let's look at other objectives briefly. I think I have about 15 minutes. Now, let's look at other objectives briefly. This is what we looked at, right? We said we want to search for something quickly with a perfect sensor, and you want to minimize the maximum time required, then it is traveling salesman. Okay? What about the next objective? If you want to minimize the average time required to find the target, this problem is called minimum latency. This turns out to be much, much more harder to approximate. I believe the best we have now is something like a 2.65 or something like that, some weird number, nothing nice like 3/2. This turns out to be much, much harder of a problem to look at, but people have looked at this again forever, right? So this has many other names. Minimum latency, I think it also goes by traveling repairman. Yeah. So essentially, the repairman wants to make sure that all of his customers are happy, right? So the total time required to, you know, uh, satisfy all the customers' orders might be high, but the average time that everyone waits is decently low.
So, just to clarify, so like you're saying average time to find the target under what distribution of the target? Is it like uniformly within any?
Good question. You can, if you do uniform, then it's the unweighted minimum latency problem.
Okay.
If you don't do uniform, you can have any discrete distribution that's weighted.
Okay.
Both of them have been studied. Both of them have approximation algorithms.
Okay, and both is 2.6.
I think so.
Okay.
What about the next one? If you want to maximize the chance that you find the target within a given time, this is huge in the on the operations research and robotics community, and this is called orienteering. Okay, so why is this a good thing to study? Well, because if you think of real-world applications, let's say you're searching with a drone. The drone, you can't say that, okay, I will keep searching till I find the target. You can't do that because the drone will die, right? It has limited battery, so you only have 30 minutes airtime, right? And what the best you can do is to maximize the probability that you find the target. Yeah.
I would assume for the last two objectives, some sort of expanding search, some random expanding search method would be the best.
Yeah, great question. That's one of the things that you could do. One of the heuristics that has been studied. Unfortunately, it turns out to be suboptimal. For orienteering, it's a complicated algorithm. Okay. All of these things are hard. Minimum latency is also NP hard, as is orienteering. I believe that orienteering does have two approximation, maybe even a p-task, following from Joe's and Sanjeev Arora's work. Minimum latency doesn't have a p-task from what I recall, but it does have like about 2.5 approximation. I don't think the 2.5 approximation is implementable in any sense. I don't know what so it went through, I think in the 70s it was about 20 or 44, the approximation factor, and then it slowly came down to what I have. I don't know what the largest implementable approximation factor algorithm is. I'm not sure if there is one. Maybe people just use heuristics to solve this, I don't know. Yeah. And actually, from what I understand, I don't think there is a simple algorithm for orienteering either. Even if it has terrible running time or anything, something that is simple to state, I don't think that exists for orienteering. I would be very interested for that actually.
So how is the time budget given? Is it like complexity or, I mean, like how do you give it? Do you like give this many rounds you are allowed to take? Or?
Great question. You can do it in many ways. What you could just say is that I just give you a rational number. Reals are weird. So I give you a rational number and be like, the total time you're allowed to take is that number, right? I give you a budget T and be like, I don't care what you do.
Okay.
Your total length is at most T. So you can do that. You can also do, and people do this for TSP, where they call KTSP essentially, where I'm just telling you that, well, tell me, my budget is that you must visit at least K points, right? So if you, the thing is that if you do it in terms of just, if I just give you a budget T, then it becomes iffy on, okay, what are your algorithms polynomial in and so on, right? You would want it to be in log T, whatever number of input bits.
Okay.
But yeah. Yeah, great question. Let me ramble for some more time and introduce you to more problems, right? I'm not going to even bother telling you solution for any of them, but I'm just going to introduce you to a bunch of problems. So this was TSP, minimize the maximum time required to find the target. But the thing here is that to search a point, you must be at that point, right? Think about the setting where you're on a drone. Well, if it's a drone, you don't have to be on it, but whatever, there is a drone. And when it searches, it doesn't really search only the point that it is above, right? It has a search radius. And that is exactly the problem we're going to look at. And what if you have a search radius? In that case, you wouldn't have to travel to V2, right? To search V2, you just need to get close enough to it, right? And how far away from V2 can I be to search V2? The radius, right? Therefore, the problem is actually equivalent to, if you just flip this on its head, to saying that I have these regions or disks on the plane, and I have a searcher who's a point instead. I'm just flipping it on its head, right? And what I must do is to get to all of these disks, right?
Now you no longer need to travel by straight lines, or?
Well, you never did.
Okay.
Even TSP, you didn't have to travel with straight lines.
It just turned out that it was.
Exactly, right? Even here, it will turn out that you will have to travel with straight lines.
Okay.
But yeah. So this problem is called traveling salesman with neighborhoods. This also has a PTAS. I think Joe gave it in 2000 something, early 2000s, if I remember correctly. 2004 maybe. But yeah. Anywho, so this has been studied as well, right? This problem is called traveling salesman with neighborhoods for obvious reasons. And here's a path, roughly how it will look like. Okay? I'm not saying any of these are optimal. I didn't actually do that. So next, what if you want to search a continuous domain instead? Right? Again, think of a drone. You have a region on the plane that you want to search. You never just have discrete points, right? So your target could be on any point in this region. How do I search it? Again, you have a search radius R, and you can fly around the region. There's no reason for you to be inside the region when you're searching it. Your search region can be outside it as well, which is okay, right? You just want to cover this region. You can do this because when you, let's say, move across, the region that you've seen is this purple guy, right? This problem is called lawn mowing, which is why I have the region in green. This is called lawn mowing because, well, this is the same as saying if you have a lawn mower with circular cutter, then how do you move the head of the cutter to cut all of your lawn? Okay? This and several of its variations have been studied as well. So, for example, you might want to make sure that you want to minimize turns in the lawnmower or something like that, and that's been studied. So here's a sample path, right? The path can go outside the polygon, that's okay. We don't really care. We are a drone, we can fly anywhere we want. There is actually also a problem which is called milling, where it's the same setup, except you're actually in milling, what you're doing is taking away regions of the plane, right? So in that particular case, you can't actually go out. But yeah, that's another problem called milling, and I don't have it here. Yeah. One more is what if you can search everything that you see, right? So this time you're not a drone. Let's say you are inside the polygon like like a watchman or something, and what you want to do is to move so that you see all of the polygons. I want to quickly put a contrast to what we looked at yesterday with regards to art gallery. There, I'm saying that I have stationary guards and I want to play the minimum number of them. Here, I'm not saying that. I have only one dude who's walking around. Right? What is the minimum length that he needs to walk?
So does that person have an area or?
So that person can see everything or guard everything that they see. Right? If they have an area that they see, that is lawn mowing. Right? If they see, if they can search everything that they see, then it's called watchman rule.
So,
Okay?
what is the initial position given in these kind of problems, or can you choose where you want to start?
Great question. We have two variants. One is the anchored watchman route, where you're given a depot, right? Where this is where the watchman has to start. In unanchored, you're not given a depot.
Okay.
The cool thing about watchman route is that to minimize the length, so here's an example, here which minimizes the length of the path that you need to take to see all of the polygons. This is polynomial time solvable, which is wild, right? Not only is it polynomial time solvable, it is solvable in decent time, like n squared or something, right? But the algorithm is not implementable at all. That's a problem for engineers. But for theory people, this is polynomial time solvable. One of the very few variants of TSP that is. And moreover, it has an interesting history actually, that one of the first few papers that talked about this problem said that it's polynomial time solvable, and then a bunch of people after that just looked at the paper and were like, cool, used it in some other setting, and then about 20 or so years later, a flaw was found in the initial papers. So then what happened was somebody else came along and actually proved it again. So the initial claim was correct, the proof was incorrect, and it was like unfixably incorrect. Like it wasn't like a small tweak and then you fix it. You had to essentially rewrite the entire thing. But somebody took the pain to actually do that. So this is called watchman rule. Again, you can have several variants. What if you have multiple watchmen? Right? Petrols. Sorry, you have a question? Cool. So, okay. So this is my last slide. I think I have a couple of minutes. I will leave you with problems of when we've only talked about perfect searchers so far. What if you have imperfect searchers? Everything breaks down. Here are some of the things that break down. First, you will never be completely sure of if you found a target or not, right? Because every time you search, there's a probability that you miss, right? And therefore, you will never have you'll never be at probability 1, right? You might have to search the same point multiple times. Everything that we did so far had none of that, right? Even in TSP, we visited a point and then left it and never worried about it again. We can't do that anymore. Next, like I mentioned, the probability that the target is at a particular point changes over time, right? Not only does it, and it changes over time as we conduct the search. It's not like somebody is giving me new information. It's just that while you're conducting the search, Bayes updates rule tells you that you have to change everything, right? So essentially the profit that you get for visiting a point changes over time. Okay? So that's my talk. I think I didn't keep you for too long from lunch. So open to questions, and I'll share the slides with the organizer and you guys can email me as well. So thank you for your attention. And see you guys around in lunch. If you guys have any further questions, we can also take some now. Yes, please.